Okay. I just want to make sure that you're aware that you're being recorded. 4K. Nope. Not at all high def. So we will talk about questions that you have in a little bit from our previous problem set. Okay, our agenda, sorry, that should say 6, not 5. So problem set 6 was your homework from yesterday from doing our lecture about titration. I'm just going to leave that. Hey, there's Olivia. Hooray. Hi, Olivia. Glad you're here, hon. So anyway, you're going to work on that set. It's just 2 titration problems. So there are 2 questions. Of course, it can't just be 2 questions. There's multiple parts to it. But that is going to be your titration set that you're going to do. And so take out your notes from yesterday. You should have labeled your paper as PowerPoint 6. This is just PowerPoint 6 continued strong titrations with strong acids and strong bases. Our learning goal for this is that you should be able to complete strong acid, strong base titration calculations. That's including finding the concentration of the unknown solution, as well as calculating the pH at all points along the pH curve, okay? So we're going to practice that a little bit more. We're also going to look at particle models. And then the last thing that we're going to look at today is indicators and how do we select a proper indicator. Okay. So if we take a look, if the pH at the equivalence point is known, an indicator can be used. So indicators change color when the pH changes, okay? So what we want to do is, for example, with strong acid, strong base, the pH at the equivalence point is 7, okay? At 25 degrees Celsius, with a strong acid, strong base under standard conditions, the pH at the equivalence point is 7. So we want to choose an indicator that changes color at pH of 7. And so in the case of acid-base titrations, one of the indicators that we use a lot is something called phenolphthalein, which goes from colorless at pHs lower than 7 and turns this bright magenta-y pink when we go for pHs above 7. Okay, so we can use this color change to let us know that we've reached that point where the moles of acid and moles of base are equal to one another. And I have a video here, but I'm actually going to kind of just show you how this works in real life. So I'm going to switch over to my document camera. So let me unpresent. It's my document camera right here. All right. Be able to see what it looks like for you guys. So here's the world's tiniest little beaker. You guys can see that right there. And what I'm going to do is in my beaker, I'll put this down just a little bit lower so you guys can see it better. You guys see the beaker okay? So there's my beaker right there. And what I'm going to add to it is a solution of acid, okay? So this is hydrochloric acid, which is a strong acid. And I'm going to add several drops to it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So the volume that I just added of acid was was that 30 drops? 30 drops. Okay. Now to it, I'm going to add something called a phenolphthalein indicator. It has a crazy long name. So phenolphthalein is PhenolPHTHALEIN, phenolphthalein. So big, long, crazy name. But what phenolphthalein does is it changes from colorless to pink. when it goes from an acidic solution to a basic solution. So I'm going to put 1 drop in there. 1 should be enough for such a small. I'm going to stir it around so it's completely mixed in. Okay. So what I have is 1 drop of phenolphthalein in there with 30 drops of acid. The acid that I'm using is a strong acid. It's HCl. Okay. Now, what I'm going to do is I'm going to add drops of base to this. Okay. And the base that I'm going to be using is NaOH, which is sodium hydroxide. Okay. And I know that this sodium hydroxide, I can look right on the side, is 2 molar, or sorry, 0.2 molar. Okay. So I want to know how many drops that I need to do to get to the equivalence point. So what I'm going to do is I'm going to slowly add drops of my sodium hydroxide. So 1 drop. And do you guys see that it flashed pink for just a quick second? 2 drops. 3 drops. 4 drops. 5 drops. I'm going to give it a little stir. You see when I stir, it goes away. So we were at 5, right? Help me keep track. This is 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, and now can you guys see that the pink is starting to persist a little bit longer? So we got to 19 drops. Let's see, we may have hit it. We're going past it. There's 20 drops. So we went to a really dark pink. That's too pink. So 19 drops is probably where we actually reached the equivalence point. When you get this really dark pink color, that means that you've gone a little bit past the equivalence point. But what that tells us is it took us about 19 drops to get there. So we could actually use this to figure out what our concentration of the HCl was. Okay. So what we can do here is we have our volume in drops. So 30 drops. If we multiply that by our molarity of our acid, we can set that equal to, oh, yep, thank you. So I can take my volume and multiply it by the molarity of my acid, and I can set that equal to my volume of my base, which was 19 drops, times the concentration of my base. Okay. And I should be able to find the molarity of my acid. Where's my calculator off to? And so what this will tell me is that the concentration of my acid, so if I do a little bit of algebra, right, divide by 30, by 30, and so the molarity of my acid is roughly 0.13 molar. And if I look, oh man, I'm off the thing because this is down so far. Here we go. So that means that the molarity is going to be 0.13 molar for my acid. Okay. So a shortcut method to figure out what we would have at the equivalence point is we can use this equation volume of acid times the molarity of acid equals the volume of base times the molarity of base. And so, yes, we use drops, which is not like a typical volume that you normally would use, but because they are both in the same unit, those drops will cancel. And so we ended up with 0.13, and I will show you on the label of the acid. So I actually do know the concentration of this. If we look, that's not so bad. The actual concentration of the solution was supposed to be 0.1 molar. And so if we look at and round for significant figures, 0.1 molar, we got pretty darn close, right? So what I just did on a really, really tiny scale is what's called a titration, okay? I knew the concentration of my NaOH was 0.2. I could see how much I needed to get to the point where I got the color change. And then I could do my calculation to figure out my molarity of acid. And then we verified it and we could see that it was really about 0.1. Okay, so this is microscale. On larger scales, you can use what's called a burette to dispense the base into the acid or the acid into the base. But this was a real titration that was done right here. Okay, this would just be considered microscale. We're doing it on a small scale. So what we're going to do today is we're just going to review and make sure that you fully understand how to do all of the various calculations that we need to do with a strong acid, strong base titration. I also want to make sure that you fully understand what a titration is and all of its parts and its purpose before we do a titration that will be more complex, because we're going to be looking at weak acids and weak bases. I just don't want to spill it. Okay. So here we go. So your notes from yesterday, again, we're going over PowerPoint 6. So your homework is to do problem set 6 and check the answers with it. And we're going to do a few more sample calculations from that. So again, if the pH of the equivalence point is known, we choose an indicator based on that pH. So what we're going to really do, indicators are actually weak acids and weak bases. So we choose an indicator with a pKa value that matches the pH at the equivalence point. Okay, so in the case of the titration that I just did, because that was a strong acid with a strong base, okay, the pH at equivalence is 7. So strong acid, strong base, pH at equivalence equals 7, okay? That pH will be different if we're using a weak acid or a weak base. But for strong acid, strong base, the pH at the equivalence point is going to be 7. What we're going to talk about coming up on Friday and the start of next week is how do we know what the pH would be at the equivalence point if it wasn't a strong acid, strong base, okay? And so we're going to talk about what's called a buffer. So that's what we're looking at there. So an example problem, so for the strong acid, strong base, if the pH at the equivalence is 7, we would look for an indicator with a pKa equal to 7, okay? So when we choose phenolphthalein, it has a pKa pretty close to pH of 7, okay? So here's an example problem. When titrating a strong acid with a strong base, the pH, the equivalence point is 7. Would bromothiamyl blue be a good indicator to use? What do you guys think? So here's the Ka of bromothiamyl blue, but we need to be able to compare the pKa. So how are we going to get a pKa if we're given the Ka value? What are we going to need to do to make that happen? Emily, do you know how you go from a Ka to a pKa? Other way around. Negative log, yeah. So that's okay. So when we talk about P stands for negative log. So when we say pKa, what this is really saying is take the negative log, right? That's what the P stands for, of the Ka value. Will give you your pKa. So the P is the negative log part of the Ka, will give you pKa. That's what that is. So yep, we would take the negative log of 1 times 10 to the negative 7th. And the negative log of 1 times 10 to the negative 7th, the log part gets rid of this base 10, the negative gets rid of the negative there, and so that would be 7 is equal to the pKa. So the pH at the equivalence point is 7. Our pKa of bromothymol blue is 7. So would this be an appropriate indicator, Emily? Yeah. Yep, they match. Okay. So the answer to this would be yes. BTB is a good indicator because the pKa of BTB is just the shorthand for bromothymol blue, is equal to the pH at equivalence. Okay, so yes, BTB is a good indicator because the pKa of BTB is equal to the pH at the equivalence point. This is quite often part of a free response or a single multiple choice where they'll say, okay, here, look at the graph. What's the pH at the equivalence point? Which of these following indicators would be good indicators? And they would give you the pKa of each, and you'd have to choose. Okay. So that's choosing indicators. Okay. So this is what we talked about yesterday. Things that you need to be able to calculate in the titration, right? This is our checklist of all the things that you should be able to do. Yesterday, we looked at a titration of an acid with a base. Today, we're going to look at a titration of a base with an acid being added to it. Okay. So you should be able to calculate the initial pH of the acid or the base in the beaker. You should be able to calculate the pH at the halfway point, meaning halfway to the equivalence point. You should be able to calculate the pH at the equivalence point. You should be able to find the concentration of the unknown acid or base that you are titrating. And then you should be able to calculate the pH at the point beyond the equivalence point when we have excess acid or excess base. So those are all the places that we should be able to do that. Okay, so we're going to go through and we're going to talk about how to do that. So if we take a look, it says you have a 25 milliliter of 0.5 KOH, and it should say it took, or to try titrate it was 0.2 molar HBr. Determine the initial pH of the solution. Okay, so in this particular case, it says we have 25 milliliters of 0.5 KOH, and we look to titrate it with 0.2 HBr. Okay. So with this, that means our starting solution is my 25 milliliters of 0.5 KOH. Okay. So the first thing we need to ask ourselves is this an acid or a base that we're starting with? So Ethan, are we starting with an acid or a base in our container?
A base.
Yep, we're starting with base only to begin with. So if we're starting with a base only, what would you predict the pH to be? Would you predict it to be less than 7 or greater than 7 to begin with?
Less.
If we have a base?
Oh, no, greater.
Greater, yeah. All right. So because this is a base, we can predict at the start our pH is definitely going to be bigger than 7. Okay, so our pH is definitely going to be greater than 7. We need to figure out what that pH is going to be. Okay, so it says determine the initial pH of the solution. So it's asking us to figure out what is the pH of our 0.5 molar KOH solution. Okay. So we have a 0.5 molar KOH solution and we want to know its pH. So what are we going to do to find the pH of this? This is the type of calculation that we did on day 1 of this unit. So Pamela, what are we going to do to find the pH?
In order to find the pH, we'll have to get 14 and subtract 500.
14.
What do I have to do? I think I got lost.
That's okay. So the first thing that we see is KOH a strong base or a weak base?
It's strong.
It's strong, right? It's a group 1 metal and an OH, so it's strong. So that means we're going to get 100% dissociation, right? This KOH is going to completely separate into K plus and OH minus. What is the concentration of KOH that we're given, Pamela?
500.
0.5, yeah. So
0.5, yeah.
Yep, that's okay. I can tell that there, I'll make the decimal a little bigger looking, right? So if this is the molarity of KOH, what's my concentration of OH going to be? If it 100% dissociates. Keep in mind that it's a 1-to-1 ratio.
It'll be the same.
It'd be the same. Okay, so what this means is this 0.5 is our concentration of OH minus is equal to 0.500 molar, right? So that's my concentration of hydroxide ions to begin with. So how would I find the pH now that I know what my concentration of hydroxide ions are? What would I need to do, Pamela?
We'll have to do negative log of OH.
Good. So we're going to take negative log of our OH. So I'm going to do negative log of 0.5. Okay, so negative log of 0.5 gives us 0.301. Is that a pH or a POH, Pamela?
That's our POH. In order to go to the pH, we'll have to do 14 minus.
Yeah, so now we're going to do that 14 minus. Yep, so we're going to do 14 minus 0.301. Okay, so 14 minus our 0.301. So that is, if we round this, is going to be 13.7 is our pH to start with. Okay, so 13.7 is our pH to start with. So we're going to start up high in the beginning, right? So we're going to have a pH that's going to begin relatively high. All right, so then that's that part there. So the next thing that we need to be able to calculate is determine the pH at the halfway point, okay? So we're starting with a pH relatively high, and it's going to go low, okay? So this is kind of the shape that we have for acid-base. The equivalence point, I didn't do the best job of drawing the curve here. Equivalence point is going to be roughly here. So the halfway point is halfway between our initial and our equivalence point. So this would be the half point. So when we talk about halfway, that is halfway between our initial starting value and our equivalence point, okay? So what's special about the halfway point, that means half of the concentration of our base is gone at that point, okay? Or half, sorry, not concentration, half the moles of our base is going to be gone. Half the moles of OH ions are consumed. Okay, so half of them will be gone. So again, it says we had 25 milliliters of 0.5 KOH. How would we figure out what half the total number of moles of OH are going to be? What would we need to do to make that happen? Annika, what are we going to need to do? Yeah, so we're going to take this volume and this molarity of our KOH and we're going to convert it to moles. So 25.0 milliliters times our 0.5 moles over 1 liter. And so that would be 12.5, right? 5 times. Okay, so this is the total. Okay, that's what we had to begin with. So at the half equivalence point, or halfway to the equivalence point, half of these moles of OH are going to be gone. So what we need to do is take this number and divide it by 2. So if we take this 12.5, which is the total, divide it by 2, that would equal half the amount, right? So 12.5 divided by 2 is 6.25. So that's the number of moles of OH that we have left. But in order to do pH, we need a concentration, not just number of moles. So we need to figure out what is our concentration of OH minus. So remember that concentration is molarity, and molarity is equal to moles over liters, right? So in addition to knowing the number of moles that we have, we also need to know the volume. So what is going to be our total volume is going to equal the volume that we had of our base to begin with. So our volume of base, which is 25 milliliters, plus the number of milliliters of acid that we had to add. So we need to know that volume of acid that we had to add to this to get to the halfway point. And so what we need to do then is figure out the volume of acid that it took to consume 12.5 millimoles of hydroxide. So how are we going to do that part? What are we going to do to solve that part? Olivia, what are we going to do to solve that part? To figure out the volume we needed of this 0.2 molar HBr to consume 12 moles of, or 12 millimoles of our OH. What are we going to need to do?
I'm gonna be honest, you're calling me every time I don't know what to do.
Oh no, I don't do it on purpose, I swear. But it's also a good thing because then I can show you how to do it so you know how to do it in the future.
Yeah. We did this yesterday, right?
Mm-hmm. We did do this yesterday. So another way to think about concentration is moles over liters, right? So that really means we have 0.2 moles over 1 liter, right? And we're trying to figure out volume. So if we look, we would have consumed 6.25, right? 6.25 millimoles of OH, right? That's what we had to consume so that we only have 6.25 left. So we consumed 6.25. Oh no, Drew, I'm sorry that happens to you. I promise I'm not doing it on purpose. So if we have 0.625 millimoles of hydroxide is what we had to consume, okay? That means that we would have used that many millimoles of H plus as well, okay? So what we want to do is say what volume of HBr would provide us with 6.25 millimoles of H plus. So if we look at this, guys, really all you need to do is let the units set your problem up for you. We want to cancel moles, and we've got this guy over here, right? 0.2 moles over liters. So if we put moles on the bottom and liters on top, that's going to leave us with a volume, right? So I'm going to do 0.2 moles for every 1 liter. And so if I multiply this, 6.25 times 1 divided by 0.2, that means that we would have needed 31.25. And see, the moles cancel, but the millis don't. So this is going to be milliliters, right? We leave the liters and then the milli part stay. So it took 31.25 milliliters of acid was added. Okay, so let me walk through those steps again. The reason why I use the 6.25. So the half equivalence point is where half of the moles of whatever we're titrating is gone. So in this case, the thing we're titrating is a base. So half of the moles of base are gone. So our total number of moles of base was 12.5. Half that number is 6.25. In order to make the 6.25 go away, we had to combine it with 6.25 millimoles of hydrogen ions, okay? And then what I had to see was, okay, what volume of HBr would provide me with 6.25 millimoles? So I took that millimoles of hydrogen ions and I multiplied it by the molarity, but I put the number of moles on the bottom and the number of liters on top, because I'm canceling out this unit of moles so that I can get a volume, which is milliliters. So now I know my volume of acid that was also added to it. So at the half equivalence point, the volume in the container is no longer 25 milliliters, it's the 25 milliliters of the base plus the additional 31.25 milliliters that I added to the container, okay? So when I put that together and simplify this equation, that means that I have 6.25 millimoles remaining of my OH floating around in 25 plus 31.25 for my total volume. So 56.25 milliliters is the total volume. Oops, cut out at the bottom. So if I divide that, 6.25 divided by 56.25. This now means that the concentration of OH that I have left is 0.111 molar. And again, this is concentration of OH minus. We're not done because it didn't ask for what is the concentration of the ions. It asked us for what is the pH, right? So how are we going to go from concentration of hydroxide ions back to pH? Drew, do you remember how to do this? I hope I didn't just make you forget everything.
You take
How am I going to do it?
negative log of it.
So we're going to take negative log of my 0.111, and that's going to give me pH or POH, Drew?
POH.
Perfect. POH. So negative log of that. So negative log, second answer. That's a pH of 0.95. Or sorry, POH of 0.95. And then we have POH, but we want pH. So what's the last step that we have to do then, Drew?
14 minus that.
Yep, so 14 minus my 0.95. So 14 minus 0.95. So now my pH is 13.05, okay? And we can see that the pH did not move very much at all. It went from a pH of 13.7 to a pH of 13.05. It did decrease a little, but not much, which is why in this first part of our graph, it almost looks like a straight line. Not much change in pH whatsoever. Okay? Any questions with that? All right. So the next one, you guys are going to like the next one. What is my pH at the equivalence point? So if I look at my line, right, it creeps along and then we get this dip. That's a much better drawing of this thing. Okay, so we get our dip here. So at the equivalence point, what is the pH going to be? It's okay, Drew. So if we take a look, here's our equivalence point. What is the pH if it's strong with strong? What is that pH going to be? The pressure, like it must be a pressure cooker when like I'm randomly calling on people. What is the pH going to be? Emily Augustin.
Is it 7?
It is 7, absolutely. So what's nice is no calculation needed. pH of a strong with strong, and this is only strong with strong, is going to be, yeah, lucky number 7 on, absolutely. So when it's strong with strong, to determine the pH, that's just going to be 7, okay? Again, keep in mind, this is only true of strong with strong. I know I keep saying that over and over and over again, but we're going to see on Friday that when we have weak acid or weak base, strong with strong, or the pH is no longer going to be pH of 7, and we'll talk about why. All right, so then it says find the pH after 150, nope, lies. Let's go on to this next one. It says find the pH after 700 milliliters of HBr has been added, okay? So find the pH after 700 milliliters of HBr has been added. So again, here's our curve. The equivalence point is here. So at this point, we should be down in this region here. So it says find the pH after 700 milliliters of HBr are there. So we know from earlier, right, our very first calculator, when we were looking at the half equivalence point, we found the total number of moles of hydroxide that was in here, right? We know the total number of moles or millimoles of hydroxide that are in the solution. And we did that by taking the volume of our hydroxide times its molarity, and it told us we had 12.5 millimoles of hydroxide. So 25.0 milliliters times our concentration of that base. So that's 12.5 millimoles of OH minus, okay? Now, when we add 700 milliliters of our acid, right? So here's our 700 milliliters, and this is our acid. It has a concentration of 0.2. So how many millimoles of hydrogen ions did we just add to the solution? How would we figure that out? How would we figure out the number of millimoles of H plus we just added? Ami, what would we do?
We would divide. No, wait, hold up.
So how did we figure out the millimoles of hydroxide ions? We took the volume of the base and we multiplied it by its molarity, and that gave us. So what would we do for the acid?
For the acid?
Uh-huh.
Wouldn't we do
how would we figure out the millimoles of H plus?
Oh, we could. What was it again? I forgot.
So Ami, look at the math right here. To find the millimoles of hydroxide, We took the volume of our base times its molarity.
Mm-hmm.
So we've got a volume of our acid and its molarity. Could we use those again to find
we
the
can do the same
millimoles?
thing.
Yeah, so we're going to do the same. Because this is a strong acid, right? This is strong. We know that it's going to dissociate 100%. So the concentration of HBr is the same thing as the concentration of H+.
Mm-hmm.
So we're going to take our 700 milliliters of our acid times its molarity, which is 0.2
Over 1.
over 1 liter, right? So that's my moles. Sorry, this is moles too. And then when we multiply that, we're going to end up with, so 700 times 0.2 is going to give us 140 millimoles of H+. Okay? So what that means is floating around in our solution, we had 12.5 millimoles of OH, and now we are adding to it 140 millimoles of H+. Okay? So what's going to happen to these moles of hydroxide? What's going to happen to them? So if we look, we're going to have, so what happens when we add H plus OH minus together? What do they make? Emily Krukowski, what do they make when you have H plus and OH together? HOH, also known as liquid water. Yep. So they're going to form H2O. So what this is saying is we have 140 of these, and we have 12.5 of these. So what's going to be completely consumed? The OH or the H plus? What's going to be completely consumed, Emily?
We also have 12.5.
Yeah, so we're going to completely consume those hydroxide. So we're just going to subtract these two, right? So my 140 minus my 12.5 from my OH, because we're going to take 12.5 moles of hydrogen to go with these 12.5 moles of my OH. And what's going to be left over is all the excess H plus. So 140 minus 12.5. Okay. So 140 minus 12.5 means that we're going to have an excess of 127.5 millimoles of H plus. Okay, that's what's going to be left over is 127.5 millimoles of H plus. All right. So how are we going to get to pH from here? What are we going to need to do? Lisa, do you feel well enough to talk today?
Yeah, that's fine.
Okay, cool.
We're
So what would we need to do next?
We're going to divide the millimoles by the amount of total milliliters.
Yeah, yep. So we're going to take our total volume. What is our total volume going to be equal to? What two things do we have to add together?
The amount of KOH and HBr.
Yeah, so we had 25 milliliters of the KOH plus what is our volume of the base that we added?
700.
Okay, so that's 725 milliliters. So we're going to take our 127.5 millimoles of H plus, and we're going to divide that by 725 milliliters. And so that means that our concentration is 0.1758. So we'll call that 76 molar. And that's my concentration of H plus, right? So how would I get the pH? What would I do next then, Lisa?
You would take the negative log of that.
Okay, so I'll take the negative log of my answer, and I get a pH that's really darn low. That pH is going to equal, it's on the screen, 0.75 for my pH. And that makes sense because we had a whole bunch of extra acid left over in there. And so this would explain the shape of the curve when we're titrating a base with an acid. Okay. Good. Any questions on these? Real quick, we're going to take a look at some particle models. Sorry, did anybody need another second with this? I just snatched it away. I know there was a lot of writing. Anybody need another second? So what we're going to do is we're going to look at some particle models. This is one of the ways that the AP College Board likes to assess your knowledge on titration, especially with multiple choice, is with particle models. And so what it's showing here is open white circles represent hydrogen ions. The gray circles represent chlorine ions. The dotted and open white circle is hydroxide. And then the dark black, those are sodium ions, so Na. And it says, we have 4 different diagrams down below here, okay? And it says, based on the information, so we'll call this diagram, this is diagram 1, 2, 3, 4. Those are diagrams 1, 2, 3, 4. And up above, what it's talking about is it says we have a 60 milliliter sample of 0.1 HCl. It's titrated with 0.1 NaOH, okay? So we have HCl being titrated with NaOH, okay? So keep in mind when these react, the products of this reaction is going to give us, so the Na and the Cl are going to go together to make NaCl. And then the H and the OH are going to get together to make H2O. So when you add a strong acid and a strong base together, you literally make salt water when you put them together, equal moles of them. Okay. So we're going to get NaCl created. And then it says, based on the information in the pH curve shown above, label each of the following diagrams as points A, B, C, and D. Okay. So what we need to do is look down below and see which picture would represent each of these. So at A, what is the only thing that's in our container at point A? Annika, what's the only thing that's in our container at point A? HCl. So at point A, the only thing that's in there is HCl, okay? So initially at A, we have HCl, and we know that that's not really what it looks like in solution. It's actually going to be separated as H plus and Cl minus, okay? So at A, the only thing that's in there is our acid HCl. So which particle model then, Annika, would represent point A? The second one, okay? So the second one is representing point A because all we see in there is Cl ions. So each one of these are Cl. Right? So all we see are Cl, and then the white open circles, those are my H plus.
Miss, can you move down a bit so we can see the full diagrams?
Yep. Sorry about that. Thank you. Right? So then we would see that each one of these are my H plus. Okay. So the only thing that's in the solution are Cl's and H pluses. So this is what it would be initially. Okay. So then if we take a look, let's look at point B. So at point B, what does point B represent? So what do we call that point B? I feel like I put everyone on the spot, but Ethan, what does point B represent? What do we call that?
Isn't that the start of a halfway?
Yep, so this is called halfway. So B is our halfway. And what's going on at the halfway? So Ethan, what does that mean in terms of our concentration of H plus at the halfway? Is it the same as it was initially?
No.
No. What is the constant? Or sorry, what is the number of moles? Is it the same or is it less?
It's less.
Less by how much?
Half, right?
Yeah, half the number of moles. So this means that half the number of moles of my H plus ions are going to be gone. Okay. Now, to get it to do that, we also had to add some base to go in there. So keep in mind that our base is Na plus and OH minus, okay? And that our acid was H plus and Cl minus. So which diagram do you think is going to represent the half? And we'll stop here and I'll go over the answers later tomorrow. So Ethan, what do you think? Which one of our pictures do you think represents the half equivalence point?
I think it's 4.
It is 4. Good. Because at that point we can see half of our concentration of our H's are gone. So that is going to be B. Okay. All right, guys. So make sure that you are joining our meet tomorrow at 1 o'clock. I will record it in case you guys have a conflict, but I will see you tomorrow at 1.